Hi, I'm Chem's best friend. If you need chemistry help, the information how to contact me is on the bottom of your screen. Hello, welcome back. And the story continues. Last time, in a previous video, we talked about Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger and their contributions to try to answer the questions, where are electrons in an atom? Remember, Rutherford, when he did his gold foil experiment, he said that most of the atom is empty space and there's this tiny, tiny nucleus. But electrons are flying around in this empty space. Where are the electrons? So let's keep going with the story. Let's go to my screen. So last time we talked about Erwin Schrödinger. Schrödinger came up with this intricate wave equation of a wave for an electron, very intricate equation. And he discovered if you square that equation, you will get probability maps, 3D areas of probability of where electron is most likely to be found. And these are different shapes of these probability areas, of these probabilities 3D shapes. He also had all these quantum numbers, and in a way there was also a restraint that the first principal quantum number can only be whole integers. The second one has to be n-1 going to 0. So this is your angular momentum. Then there was the magnetic quantum number, and that is the way you can put the orbital into space, how you can orient it. And they can go only from negative L through 0 to positive L. So there were restraints of what numbers can be. And he also noticed that there were these distinct areas where probability went to 0 of where to find an electron. So he comes up with this idea of energy layers, of energy shells. And that's the same as the Russian Matryoshka dolls, where they stack one inside another. I need you to keep that in mind. So what does this mean? How are we going to go forward with this? Well, let's keep in mind our table. So first energy layer, right, can have only one sublevel, and this sublevel, we call it 1s. So here it is. First energy layer can only have one sublevel. Second energy layer can have two sublevels. Their values are 0 and 1. That corresponds to S and P. There is one way of putting S in space and three ways of putting P orbitals in space. Here is your second layer, and here is its two sublevels. I colored them yellow and blue. Here is my two sublevels. S orbital can have only one way of putting it in space, and here are my P orbitals. Third energy layer can have three sublayers right here. The values 0, 1, and 2. 0 corresponds to S, 1 to P, and 2 to D. So you can have S, P, and D orbitals. And there is one S orbital, 3 P orbitals, and then right here you can see there's 5 values. So they can be 5 D orbitals. Right? So this is what it means. So this is just one more case. Let's look one more time at this. S orbitals are just spheres. There's only one way of putting sphere in space. P orbitals are right here. These are your P orbitals. They are like dumbbells. And there is 3 different ways of putting them in space on X, Y, or Z axis. Here is my 5 D orbitals. Most of them are 4-leaf clovers, and there is 5 ways of putting them in space right there. It's my D orbitals. These are F orbitals, and they get more intricate shapes. So some of them are like double 4-leaf clovers, some of them have 6 lobes, so it becomes more and more intricate. But these are 3D probability maps of where an electron is most likely to be found. So this here, this looks great. Let's fill in a little bit more what it is. So I'm going to say this is my 1s, this is 2s, this is 2p, this is 3s, 3p, and 3d. Now I would like you to notice something else. p orbitals start only on the second energy layer. d orbitals start on a third energy layer. And f orbitals are right here. F orbitals right here. They start on the fourth energy layer. I didn't have space to draw all of that. Everything looks great, right? But the story is a little bit more complicated. And that means it actually looks like this. So here is S, here is P, kind of goes up. Here is, second energy layer. Here is my third energy layer. Here is fourth energy layer. And you can see the colors, how they correspond. And the reason is, when you have a lot of electrons together, they repel. So the second energy layer, the two sublevels, they will shift away a little bit from one another. So S and P will shift away. And then third energy layer, you have your S, P, and D, that will shift away. And it gets a little complicated because look, 4S is actually lower in energy than 3D. Ay, 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 how are we going to keep track of all of that? You will, don't worry. So here is another way of representing that. And here I highlighted. So here's my first energy layer, here's my second energy layer, third energy layer, fourth energy layer, fifth energy layer, here is sixth. So they do not go in a straight line. Okay, so how do we assign addresses to where the electrons are? So there are some rules we have to go over. And you have to follow these rules. Here are the rules. Rule number 1. Aufbau principle. Aufbau actually is German, building up. So what does it mean? You're going to add electrons one at a time, but you're going to start lowest energy level first. So you're going to start from the bottom, moving up. Second rule is Pauli exclusion principle. And that tells you that each orbital can hold a maximum of 2 electrons, and they have to have opposite spins. Remember, there was that spin number, positive 1/2 and negative 1/2. That's what it means. And the third one, Hahn's rule. So whenever electrons occupy equal energy orbitals, maximum number of unpaired electrons results. And I like to say that you're going to maximize same spin. All right, so that's how we're going to fill in these electrons using these rules. Let's give it a try. Are you ready? I think we are. So let's start with sulfur. Sulfur, find it on the periodic table, has 16 electrons, right? So we have to fill in 16, electrons here. So each electron will be represented by an arrow. So an arrow pointing up is electron spin up, and then there will be an arrow going down, electron going down. And another thing is each box here corresponds to that one orbital. So here we have S orbital, here we have our 3 P orbitals, yes, here is our 5 D orbitals, and each orbital can hold 2 electrons. Okay, let's start with 16 electrons for sulfur. So how am I going to fill these boxes? We're going to start on the bottom of bow. So 1, 2, and 3, 4. Now I have to go to 2p. So here I'm starting with Aufbau principle. I went from bottom, I'm going up. I have 2 electrons per orbital, opposite spins. And now I have, in my 2p region, I have to follow Hahn's rule. So I'm going to fill in like this, pointing up, 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 and then down, down, down. Yes? Okay. Then we have to go through 3s because I'm not at 16 yet. So now here I have a 12, and then 13, 14, 15, 16. Here you go. So I filled in my electrons in the orbitals for sulfur, and now I'm going to write my electron configuration. So where am I? Well, I was on the bottom energy layer. I went through 1s layer, and I have 2 electrons in my 1s orbital. Then I went to 2s, and I have 2 electrons. Then I went to 2p orbitals, and I have 6 electrons. Then I went to 3s, 2 electrons. Then I went to 3p, and I have 4 electrons. If you add up these numbers, should be, these exponents, but they're not really exponents here, it should equal 16 electrons, right? And we know that we are at the 3rd energy layer. So imagine, so we went through 1s in the sphere, there's 2 electrons are more likely to be found. Then when we went to the 2nd energy layer, and there was a sphere, 2s, 2 electrons, and then there were the p orbitals. And there was 6 electrons in a p orbitals, and then we went to 3s, and then we went to 3p. So you know where electrons are most likely to be found, in what regions around the nucleus. Okay? Let's practice a little bit more. Let's make it a little bit harder. Yes, you ready? Let's make it a little bit harder. And I picked cobalt. I think cobalt. It's a nice metal. Let's fill in cobalt, if you find it on a periodic table, a neutral atom of cobalt has 27 electrons. So let's fill in 27 electrons here. And we have to fill in using all the rules. So Aufbau, starting on the bottom, poly, 2 electrons per box, opposite spins, and Hans rule, we're going to maximize same spin. So let's go to cobalt. So, oops, let's make it a pen. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now I have to go for S, 18, 19, 20, and then 7 more. So we're going to go 1, 2, 3, 4, 5, 6, 7. And I'm going to write my electron configuration for cobalt. Well, I went through 1, S2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7. And if I add up all the numbers here on top, it should be 27, and it is. So some of you might have questions. Should I switch these two? Should I switch 4s and 3d? Should I keep all the 3 in energy layer 3 together? Or can I put that 4s here? Either way is perfectly correct. If you are taking AP chemistry, both answers will be accepted and you will get credit for both ways of writing it. So I prefer this way because it shows that 4s is a little bit lower in energy than 3d. However, notice that they are very, very close. And then later, actually, if you look in the higher energy levels, the D and F are ridiculously close together. Okay, we ready to go a little bit harder? A little bit harder. I think we are. Let's go to antimony. Antimony is 51 electrons. So, lots of counting. Are you ready? Let's go. 51 electrons. I'm just going to keep going here. We can fill them in quickly. When I have to go through 4s, I have to go through 3d. I'm doing my Hans rule, maximizing same spin. I have to go through 4p then. 4p. I have to go through 5s. And I have now to go to 4d. And then I have 5p, and I'm going to go up, up, up. 5p, 3 of them are filled in. Let's write our electron configuration for antimony. I think we can do it. Yes, we're just going to read from the bottom what we went through. So 1s2, 2s2, 2p6, 3s2, 3p6. 4s2, 3d10, 10, 4p6, and I'm going to keep going here, 5s2, 4d10, and 5p3. Notice I wasn't even counting, and I knew where to stop. So, is there a cheat sheet? There is a cheat sheet, but I'm not giving you the answer yet. That will be in the next video. However, before we go there, let's do one more challenge. Are you ready for one more challenging one? Let's go to polonium. 84 electrons. So I figured you don't want to be looking at me filling in 84 electrons, so I filled them in, ahead. So first was 1s, then I went to 2s, 2p, 3s, 3p, went to 4s, 3d, 4p, 5s, 4d, 5p, then 6s, then we're going to 4f first, then 5d, then 6p. So let's write it all down. Polonium. Wow, that's a long one. Let's go. We can do this. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Where am I? 4p6. All right. 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p. How many? For polonium, 1, 2, 3, 4. And there you go. So some of you are wondering, is there a cheat sheet? What happens if I don't get this chart with me on a test in school? Chances are you will not have this chart in front of you in school. How do you keep in track? How do you memorize all of this? Also, this is quite a mouthful to keep going. Is there a shortcut way? Is there a way? Yes, it is. But the answer for this is coming up in the next video. So thanks for watching and see you next time.